All right. Welcome back to another HPL seminar. Today we have a very special guest, Dr. Michael Slawinski. He is currently a professor in the Department of Earth Sciences at Memorial University, Canada, and he is also a visiting professor at the Department of Mathematics at the, I'm going to say, Polytechnic Institute of Milan in Italy. That is, he currently resides in Italy primarily and bounces back and forth between Canada and there. Dr. Slawinski received his PhD in seismic anisotropy in 1996 from the University of Calgary. And then he spent, I don't know, what does it say, 10 years working in oil and gas as a geophysicist. Currently, so during that time, in 1997, he founded the Geomechanics Project at the University of Calgary, which is an interdisciplinary group composed of graduate students, postdocs, research associates from physics, math, and computer science. And their work focuses on inverse problems and material properties within continuum mechanics, with emphasis on elasticity theory and its generalizations. Recently, during COVID, he became interested in modeling, in the similarities between modeling geomechanics and bicycle performance and power outputs on the velodrome. And this is what he's going to be talking to us today. So it is my pleasure to introduce our guest.
Here we are. You saw 1 minute of 1 hour, but you saw the very beginning and the very end. I'm going to describe how those things are prepared and how they happen. I don't know if you could hear me well. I have a microphone, so I go to the next slide. Power for the hour, mathematical modeling of performance on velodromes. Here we are. Let me first tell you a few things back historically. But before I do so, I would like to tell you what kind of a model we do. What we are doing is a phenomenological model. That means that it is a scientific model, but it's not derived from first principles. So let us read maybe what I wrote here. A scientific model that describes empirical relationships among phenomena in a manner that is consistent with fundamental theories, but not directly derived from the first principles. We're not going to quantum mechanics to derive it. What we do is that we certainly cannot do something that would not be true physically, that would be in contradiction with physical laws, but we are free to make a number of assumptions. For instance, we formulate, as you will see in a while, that the resistance of the air is proportional to the square of the speed. Force of resistance of the air is proportional to the square of the speed. It's not a fundamental statement, but a statement that makes sense. I'll show you in a moment. We invoke selected principles and laws in our formulation. For instance, if we don't need thermodynamics, we'll not invoke thermodynamics, or at least we feel we don't need it. One can sometimes be surprised and find out later that one did need it, but one chose not to use it. One describes relationships among variables without searching for an explanation. We say, for instance, that something, like I said a moment ago, force of the resistance of the air is proportional to the square of the speed. Why? We don't worry about it. Why? It works in a sense that is empirically adequate with our measurements and also is consistent in a certain way with our formulations. So that's what I wanted to say, that that's the type of a model we are doing. And I presume that all of you in the field in which you are, you all do those kind of models, except somebody truly saying quantum mechanics or fundamental physics. All the models we do are of that kind. What I'm talking now about, and I will go through not too many details, but if you are interested in details, you can always ask me afterwards, of course. But what I'm going to be presenting is based on the work that we've been publishing on archives for the last few years. You might notice that archives, one of the advantages of the archives, as you probably know, is that you can update your papers. So here you see paper is version 12. It's version 12 of that paper, which means that whenever we learn something more, we find out something different, we include it in the paper and we update it up to one done on here last March, version 12. Historical comparison. Let us think about it for a moment. The idea of an hour record is quite famous, both in running and in cycling. It's more than a century old. I just put a few selected things here. Say in the case of the runs from 1928, we have Paavo Nurmi, famous Finnish runner, who did 19 kilometers and 210 meters in 1928. The much more recent one in 2020 was 21 kilometers and 330 meters. The difference between them, the late 20s and 2020, is about 11%. Let's look at cycling. It also started before that, but I just started with Giuseppe Olmo in 1935 and Filippo Ganna, who will be the main topic of our conversation in 2022. The difference is 26%. What is the reason for the difference? Well, in part is technology. Technology in the sense that we have a bicycle as opposed to not having a bicycle. Of course, the surface of the running track changed, the shoes changed, so that improved it a bit, and training schedules became more optimized. But the difference is to a large extent because of technology, but not only. Also the strategy. How do you strategize your hour record? How do you strategize in a sense that you don't start too fast and then the last quarter of an hour or so you decide that you really are done? Or you finish an hour thinking, I could have gone harder. Because you have to remember, that's a statement of a friend of mine who had the record before Filippo Ganna, Dan Bigham, who said, half an hour is not half of the hour. And that's true. The second half an hour is something very, very different. So it's easy to go too fast at the beginning and then collapse, or be too cautious and not give everything. And that's where our mathematical model comes in, to strategize, to optimize. That's precisely the strategy that we are talking about. Here is Dan Bigham, who had the record before Filippo, and he's also a race engineer for Ineos, which is the team where Filippo Ganna is. And the three records that he did within less than a year, in October 2021, he did 54,723 number of meters in 1 hour. They were all in Grenchen, the same velodrome in Switzerland. Then in June 22, he did a little bit better, 52,1216. And then in August, that's his best time so far, which was the world record officially at that time. The one before was also a world record, but we were doing that for the sake of measuring the things in a manner as to optimize the performance when all the referees are called, where all the judges from the union are formed there to ensure that it's truly a record that can be recognized with all the details. And that's his record now. Now, within less than a year, did he improve so much? Well, technology didn't, probably. Him, as far as the improvement, he can maybe tell us. He's right now in Toronto, in the velodrome in Toronto, and he might be watching this talk. So, Dan, if you are watching this talk, don't hesitate to comment on it afterwards. But what I wanted to say, that at least a portion of this improvement is an optimization, is to know how to go, how fast to go to be able to really be spent by the end of the hour, but not before. I have to learn which direction. The key formulation for it is something that started about 3 decades ago: power meters. Power meters for the bicycles. That is really what allows us to make this formulation. Here is power meters from the company that is to a certain extent supporting my research, an Italian company, Favero. And the power meters work in the following manner. I'm going to describe it to you briefly. Power, from a physical point of view, the most common way of us talking about the power is the ratio of work divided by time. The shorter time it takes to give the same amount of work, the greater the power. So the denominator T is smaller, W stays the same, P grows. It's also linked through its units, as you can see below, is linked very nicely to the concept of a bicycle. Is the force that is against riding of a bicycle multiplied by the speed with which the bicycle is moving. Still something not easy to measure. But it's also the same thing as the force applied to the pedals. So you can see that you apply force to the pedals here with your shoes, multiplied by the speed along the circumference of your pedal. So you can measure the power needed to overcome the resistances to move at a certain speed simply by, it's not so simple from the technological point of view, but conceptually simple, by multiplying the pressure on the pedals, the force on the pedals, time the speed of the rotation of the pedal, not the angular speed, the speed along the circumference. That's why the crank, the length of the crank matters. If it was a rotational speed, it wouldn't matter. Whenever we do a model, it's important to know whichever model we do, it's always an approximation within the realm of mathematics. One of the key things we want to know about approximations is how much we lose by making a simplification. We want our model to be simple, to have as few parameters as possible. Simple, but not simplistic. So we look into more accurate formulations and then see, can we give up on certain things and still be, as philosophers of science would like to say, empirically adequate. Here's my doctoral student, who is actually, I know he's watching this from the East Coast, so he might comment on it afterwards, especially if you have any questions, or if he wants to comment something on it. He did a very nice study of the shape of a velodrome, which from the mathematical point of view is differential geometry. And in the way that he did that, that's his velodrome. And that's a quarter of a lap of a velodrome. And you can see certain things very clearly here. Of course, you see the banking of the velodrome. And the banking is a ruled, or velodrome in general, is a ruled surface. That means that you have straight line that changes the inclination. So it's different inclination here, about 13 degrees, and different here, about 46, but at each point, if you were to go perpendicular to it, it would be a straight line. People sometimes, when they look at the velodrome, they think it gets steeper as you go higher up. It doesn't. It's a straight line. So the leaning of the velodrome, or the angle of the velodrome, is as much here as it is near the bottom. That's what it means that it's a ruled type of a surface. And then he did a number of formulations, which I am not going to talk about in details, but there's another paper in arXiv that he did. And from this, we divide a velodrome into 3 parts. We have a straight, we have a curve, which is a part of a circular arc, and we have a transition curve, which is extremely important. It's particularly important on the train, which you are on a rail. That means when you're going from a straight line where the radius is infinity to a part that's an arc of a circle where the radius is, say, 25 meters, you want this transition to be smooth. You don't want to go straight from an infinite length of a radius on the straight to a 25-meter radius on the arc. So you have a transition zone, something very important in the trains, because if you don't have it on the train, you would have many trains that would be derailed or be very uncomfortable for the passengers. Actually, what you are doing to do that, I'm not going to go into details, but you look at the third derivative of position with respect to time. So the first one is velocity, second one is acceleration, and then you look at the third one, that in English is called a jolt, and in American is called a jerk, which is the third derivative of it. So here we are, but what we decided, trying to simplify it, of course, we do it in such a way that when we add straight, transition, and the arcs, we have to come up with 250 meters. What we did is that we put it basically into two-dimensional structure to make it simpler. Why two-dimensional? Because the cyclist follows the black line, the one that's on the bottom. This black line is not really horizontal because, of course, when we lift it from 13 degrees, say, to 46, this black line moves up slightly along the curves. But we decided it doesn't move enough for us to worry. And also the cyclist does not necessarily follow the black line to within a millimeter. So trying to stick to that would be an unnecessary precision that would not increase our accuracy. You could see on the picture that we saw before, Filippo Ganna would sometimes get off the black line. At the time you didn't see it, but maybe at then we can show once again this short picture, the short video, and then you will see those things. So what we did is precisely that. We have those three segments of the curve: straight, transition, the arc lengths, they sum to 250, and the radius of the arc is 23.38863. We do it up to 4 decimal point, but of course, within the model, one can also be rounding that up. That wouldn't be such a problem. A few comments about these transitions. What we are doing, that we have a curvature of 0. The curvature being, in this case, the way in our formulation is just 1 over the radius. So along the straight, we have 1 over infinity. So curvature is 0. And then over the curves is 0.04. And that's precisely, we don't want this to be a jump. We want this to be a transition that's reasonably smooth, and we did it as a cubic polynomial in our model, which is consistent with the velodrome itself. And the reason to have that is that the cyclist can follow as much as possible the black line, 250 meters, without getting off the black line so as to make a curve, because that would be akin, say, if you are running 400 meters on a track, in a running track, you want to be running in first lane, and you want to be running in such a way that you're very close to the grass of the field, not somewhere towards the end of it, because you will still be, it'll still count only as 400 meters, while you might actually run 408 meters. So that's why it's important to make this very smooth and then to allow the cyclist to follow that direction. The banking. The banking fits very nicely a trigonometric model that we do, and the one they are generally of the same type. Sometimes they might be 13, they might be 8, they might be 14, and then as far as the steepest part, here is 46, which is on the steep, which is rather steep. The one, the velodrome in Bordeaux, for instance, we have there 44. So the regulations are a little bit more flexible than in the running track. That you have to be within certain limits. The limits are small. You can say change it within a couple of degrees, but you have certain flexibility. The one in Grenchen is quite steep, 46 degrees on the steepest part, 13 along the straight line. And there's an interesting point that we assume to be 0, but as a matter of fact, it's not uncommon that this curve would not be symmetric from the point of view of the long and then the short axis of the oval. It's not uncommon to make the steepness of coming out of the curve slightly steeper than coming into the curve. But the difference is so small that for our estimate of power, it becomes negligible. Finding out what's negligible in our formulation is one of the key aspects of doing a good model. We want a model to have as few parameters as possible while still being adequate for our formulation. The other assumptions that we assume that the rider is following the black line, which is to a large extent true, but not exactly. We also assume that that we have a rider that maintains the position all the time, and we assume a steadiness of the speed of the center of mass. So we don't include, for instance, in our model, the first lap. The first lap when Filippo Ganna was starting from standstill and reaching the speed, that's excluded from our model. As is very common in mathematical models in physics, we want things to be smooth, operations to be smooth. We want our things done in such a way that we can assume a variety of things that will be more complicated if we entered into accelerations, if we entered into changing the direction from the black line. So there is a variety of simplifications. So we basically assume that Filippo, that's a picture of Filippo made by a friend of mine who is a cartoonist in Italy, Roberto Laucello, Lau. Actually, I happened to write a book on philosophy of science, and to make it more fun, Roberto Laucello made a number of cartoons for the philosophy book. So he also makes those cartoons for me whenever I do something, presentations like the one for today. So that's to show the assumption of a model that we assume the cyclist to follow that pattern. The other assumption that we do, we assume that the rider is always in the instantaneous rotational equilibrium. And then you can see that the leaning of the cyclist, this theta, that's sort of a curvy theta, is the arctangent of the centripetal force divided by force of gravitation. And then where the centripetal force depends on the mass of a cyclist and the bicycle, square of the speed of the center of mass, and the radius of curvature of the center of mass. Is it a good assumption? It's not a bad assumption, but one could claim, for instance, that the assumption should be that the cyclist is almost all the time trying to regain the equilibrium by correcting very slightly the wheels. So that would be another model, probably wouldn't change very much when it comes to the results. So that's why we decided to follow that pattern. And you can see that's the way that the cyclist would be leaning up to 45 or so degrees along the curve. And this is the curve right here, the curve of the banking. The ideal thing would be to always be in such a way that you'll be perpendicular to the surface on which you are riding. Because in such a case, you would have no deformation of the tire that's associated with not allowing you to slide down or to slide up. But that's impossible to create a velodrome like that, because even riders of different type, of different height, of different weight, going at different speed would be leaning differently. So it has to be some sort of optimization for a velodrome that will welcome a variety of competitions. Dissipated forces. Dissipated forces, that's the model that we formulated. Again, if you want to see the details, how the model was done and how each of those parts came about, we have it in the archive. If you would like, I can give you exactly how to do it. But if you look for my name and archive, then you would find it there. So it's really a four parameter model. One is lambda, the resistance of the drivetrain. And the drivetrain is going to be some form of a resistance associated with crank, chain, hubs, bottom bracket. So that's where lambda goes. Everything goes into lambda. Then the resistance of the rolling, CRR, which depends on the tires that you would have and depends on the surface that you have. Deformation of the tire, which would be when the tire deforms when you are turning, but you are not turning in such a way that you are perpendicular to the inclination of the velodrome, but you are leaning towards, but there is some form of an angle. Notice here, for instance, we can see right away from this picture, theta, the non-curly theta, is the inclination of the velodrome. The curly theta is your lean. If both are equal to one another, this is zero, sine of zero, this whole thing would be gone. So that would be ideal. But you cannot really create a velodrome like that. And there is the air resistance. The air resistance, which is right here, which is the famous CDA that cyclists often talk about. And I'm going to show you how we formulate CDA times the density of the air times the center of mass speed cube. Notice there are two velocities here. There is a velocity that we mark with a small v, which is the velocity of the wheels, because that's what happens along the wheels. And here is the velocity of the center of mass. They are not the same. When you are leaning, your center of mass is moving more slowly than your wheels, because wheels are covering a distance that's larger than your center of mass in the same amount of time. So they have to go more slowly. Just to show you sort of a phenomenological model that we talk about, how one formulates the resistance of the air. So one starts with a statement saying that the resistance of the air would be proportional to the pressure and to the frontal surface area. Well, if it's proportional, that means there is some constant of proportionality. We assume it's linear, typical thing to do in mathematical physics. Let's call it CD. CD for the coefficient of drag, CD, and then PA. P, we say pressure is analogous to kinetic energy. So we just call it 1/2 rho v squared. When we put it inside here, we get this formulation right here. And then we say, another simplification. It's not easy to distinguish the coefficient of drag and then the surface area, because surface area might be changing because I'm positioning myself in a manner that's more leaning forward, but then I'm lifting my head a bit. So the turbulence before the head becomes greater. So typical thing in such a model, let's put it in a single basket. Let's put it all together as one parameter. So that's why this CDA here written with a different A, because it becomes a single parameter here. And then, as you've seen before, that power is equal to the force times velocity. That means that the power that is required for the resistance of the air is given by this expression, 1/2 CDA times rho times V cube. There's also another thing. Apart from the dissipated forces, we have conservative forces. Gravity about one of them. That's Newton, also done by Roberto Laucello. You might have heard the story, which has been quite common, but has been shown since to be false, that Newton was sitting and then an apple fell on his head, and that's how he thought of gravitation. The truth of the matter is that he was quite a cyclist, and he thought about it while sucking up the hill. He suffered quite a bit, as Roberto showed us here, and that's how he thought of theory of gravitation. So here we have it. And now the idea of missing something from a model that seems natural not to include. On the velodrome, we are riding on the so-called black line. It is black. That's apart from this tiny lift about the curve because of the surface that comes up by a dozen or so centimeters, which is negligible. It is flat. So we don't have to worry about the force of gravitation. Why would we? I mean, we are going on the flat. We shouldn't include it in the model. And I must say, all the people that I know, the models that I know before our model, people didn't. However, being most of us of the physics type, we knew that there ain't no free lunch in physics. If you are lifting your center of mass every time you're coming out of the corner, the curve, there has to be power that had to go somehow into your being able to lift your center of mass. That's Huygens, by the way, if you were wondering, if you didn't recognize him right away. That's a Dutch mathematician, physicist of roughly the same time as Newton, Christian Huygens. And he was instrumental in formulating the centripetal force. And the lean is precisely the arctangent of centripetal force and the force of gravitation. This, you will see in a moment, whether it is negligible or not. The fact that we are moving this way all the way. Before that, I'll just tell you a little bit about it without numbers, but then you will see with numbers. change of potential energy, you're lifting your center of mass, is the equation mgh, which we know very well, where mg is the force of gravity, and then delta h, change how much you are lifting vertically your center of mass, would be the cosine of theta maximum minus minimum. Minimum would be, you would be moving at 90 degrees, so it would be vertical. So cosine here would be 0, and you would have just some delta H that come from it. And your power associated with it would be counting the fact that you do it twice every lap, because you have a curve on each side. You do it twice. That's why this 2 appears here, divided by the time of the lap to give it the power, force, and the work here, and then power here. 1 minus lambda. Why? Because you gain it from your speed. And your speed is dissipated to a certain degree, maybe not very much, but is dissipated by the smoothness of the operation of your bicycle. Again, bottom bracket, cranks, hubs, and so on. So that's how this works. Now we go for empirical validation. The velodrome was, in spite of that you saw a group of people there sort of cheering Filippo towards the end of his ride, we were all put, most of people were in a small part of the velodrome, because the idea was not to make it open to the public so as to able to control the humidity and things like that. So it was really just people who were invited could go to that. But those of us who were close to Filippo when he was about to start seem to have heard that he said, "Con il modello matematico preparato mi sento pronto." With the mathematical model prepared, I feel ready. And then he started, took off, and he set a beautiful record, significantly improving on the previous record. Let us look at the input-output of the model. We have 5 slides here left. The sort of, like time down from sort of the hour when Filippo would look at the time there, knowing how much time he still has left. So we know we are at 21/26. So we are heading towards the latter part of the talk. The input, total mass, 97 kilograms. That's bicycle together with Filippo. Filippo is tall, 193 centimeters. Parameters that we chose, which are to a large extent an educated guess, other formulations, wind tunnel measurements. It's a combination of things that go into it. So for instance, CDA, as you can see here, is 0.184. It's given in meters squared because that's the surface area that gives meters squared. Then there's the rolling and the deformation. And then interesting thing that you might want to think about, lambda, which is the resistance, the efficiency of the drivetrain, we take away only 1.5%. So the bicycle is extremely efficient, 98.5% efficiency. And that's one of the reasons, maybe even the key reason, that we use fixed gear on the velodrome. If you had a free wheel, and if you had, say, gear shifts, that would be different. That would take significantly more energy. It would be much less efficient. You would have certain freedom of movement there, certain friction, extra friction. So one of the reasons, if not the main one, as I said a moment ago, for having this kind of construction that the bicycle has a fixed gear is precisely to keep the efficiency of the drivetrain so good. Center of mass was, of course, very important for us to do because, as is commonly done in physics, we did most of our calculation based on the center of mass. Center of mass, of course, is an approximation because, after all, we could take the whole body and do some kind of a calculation differently, but we focus on the center of mass. And it's 1.1 meter, which with an empirical adequacy, to bring back the philosophical vocabulary, it is coinciding quite well with the height of a saddle. So basically, if you are in that position of aerodynamic type of a position, your center of mass is approximately the same as the height of the saddle. The air density, 112, changes a lot the performance. There was, in some cases, thought that if it happens to be a very high pressure day, one postpone the attempt a day to low pressure. This, you are on a velodrome that's covered, so that's not a problem from the point of view of the rain. So you are basically you praying for rain, storms, low pressure zones, because it'll change a lot, because the coefficient that is density of the air is multiplied by the cube of the speed. So small change in this coefficient means huge change in your power. Just to give you an idea, between rather low pressure and high pressure, the difference in your performance with the same power output might be about a kilometer. So instead of covering, say, 56 kilometers, you cover 55 with the very same power output because of the density of the air being higher. And then there are some interesting things here. So the power that we did estimate, and that's consistent within the measurements to within the experimental errors, was about 460 watts. That was the average power of Filippo Ganna. That's quite a bit for those of you who cycle with the power meters, especially for an hour. And it's divided into two parts: the dissipative force, so the air resistance and so on, and the force associated with you increasing the height of, or increasing your potential energy, the height of your center of mass. Notice the difference. This is about 10%. So if you ignore that, you would be giving an estimate prediction that would be about 10% off. That's a lot. If you're telling a cyclist that to set the hour record, you need to go around 420, but as a matter of fact, they need to go about 460, that could very easily be a difference between succeeding and not, or even a difference that the person, if the person knows that 460 is needed, would say, I'm not even going to attempt it because I cannot produce that kind of a power. And then, of course, the classic thing, if you just look at the dissipative forces, which are right here, and you subdivide them, the vast majority goes for the air resistance, 390 watts. And the other three, the rolling, the deformation of the tire, the drivetrain, only 26. So you can sort of see where you should put your focus. Of course, you want to focus on everything and do it well for everything. But if you have to give up on something, you would give up rather on the tires than on the position that would be aerodynamic because of that difference. So basically, concluding or beginning our conclusion, strategy. What we want to do, we want to maximize the distance covered within an hour, subject to physical laws, we cannot overcome them, and availability of power of an athlete. One of the things that we can do is to choose the velodrome. As you know, many times one would go to the altitude to do those performances. It was very commonly done, still is, in Mexico City. So one would go there. For instance, there's also a velodrome in Bolivia at about 2,600 meters. And if Filippo was going to go there, for the very same distance, he would need 375 watts average, not 460. Huge difference. Now, there's a couple of things. Depends how you respond to being at such an altitude. There's also something that's very important, that having a schedule of races, you might not be able to go to Bolivia at 2,600 meters for a month or 6 weeks before to acclimatize because of the races that you have. The way that Filippo did it, he was just flying back from Australia, where he was participating in road world championships, to Paris, where he was participating and winning the track world championships. And that was basically a passage from Australia to France, meaning that he had a few days to do this record, not several weeks to get acclimatized in order to perform at a high level, at a high altitude. The other interesting thing, and now it's fairly standard, that the velodromes are 250 meters. The one we have in Calgary is 400. The one we have in Edmonton is 333 and 1/3. The rule is that it's supposed to be easily manageable to a kilometer. So in Calgary is 2.5 laps, in Edmonton is 3 laps. But a classic formulation now, the velodromes for the Olympics and for records like that, they are to be 250 meters. There's an interesting thing that comes from it, that when you make it reasonably tight velodrome, your center of mass is covering significantly less distance than actually the distance along the black line for which you are credited. So in the case of Filippo, the center of mass covered almost a kilometer less than the distance that his wheels covered. The wheels covered at least the distance, 56 kilometers, 792 meters, whereas the center of mass, because of its lean, covered 55 kilometers, 804 meters. And of course, the tighter the velodrome, the bigger the lean, the more this difference is going to be greater. So if you were to do it on a straight line, that would be, say, 57 kilometers, you would need more power than you need on the velodrome, where you are leaning quite a bit, and hence your center of mass is covering a lower distance. More about the strategies. Here's the distance of Filippo, 56,792, which is 227 laps plus a little bit. It's done up to a meter. So when you are finishing, for instance, there's this bell that if we put it again for you to see, you will hear there's a bell of the last lap, because we know that he will not have enough time to complete that lap, but he goes a portion of that lap and that's added to it. So it's not the number of completed laps that counts, but completed laps plus delta, whatever is on the last lap. Formally, our model is applicable after initial acceleration, which we said we won't take into account starting from standstill to reach the speed, for constant center of mass speed. But as one always does in physics, one always stretches a little bit applicability of a model. One formulates a model very commonly. We do it even in thermodynamics that I mentioned at the beginning, that we make our calculation based on equilibrium, or we formulate our model based on equilibrium, and then we allow ourselves small deviation from equilibrium that they would still be correctly described by the model that was really done for the for the equilibrium. So pragmatically, as opposed to formally, model is applicable after the initial lap that we don't take into account for small monotonic increases in V. So there are two types of strategy that we looked at, and we followed rather the strategy number 2. I say rather because it's not necessarily that exact once you're on the velodrome and on the bike, but it's been quite well done, especially by Dan Bigham, who was extremely well prepared and who focused on every detail on his formulation. You can do a steady ride. So you basically start, and after the first lap, you continue the same lap time, the same speed, and say 57 kilometers per hour will give you the record of Filippo with 460 watts, as you saw a while ago. Strategy 2 is a linear lap time decrease. So you very slightly increase your speed from the beginning. You start at about 55 kilometers per hour after the first lap, and you finish at about 59. So as far as your average is very similar, 461 as opposed to 460. So with an experimental error, you can basically say it's the same. However, since you are reaching the higher speed, 59 kilometers per hour, towards the end of your ride, your speed for the last lap must be about 511 watts. You might not have it to be able to do that. So that's an important consideration. Why would one do that? And that's something that maybe my colleagues from CORE are listening to that, and they can say more, because that enters into physiology, and I did the physics and mathematics, not physiology. Actually, something I'll tell now, I didn't know that. You probably know because of your field of studies, that our internal temperature increases significantly during this kind of an effort. That a classic temperature of our body when we are in good health is 36.6 centigrade. the temperature of inside of our body raises itself up to almost 40 degrees. So this core device is something that you attach to your strap, the same strap that you have for the heart rate monitor. And from the flux of the heat, it measures, or it estimates, it doesn't measure, but it's not inside your body, but it estimates your internal body temperature. And the idea is to keep it low for as long as possible. So to start a little bit more slowly, not too slowly, because you might not be able to pick up the pace too much, but to start a little bit more slowly so as not to heat up the interior of your body too soon. I cannot answer too many questions on it. So if Chris is there somewhere, please comment on it afterwards, because I said as much as I know about physiology. I can also say that here we did the linear increase like that. Dan Bigham, for instance, when we did it, when he did our record, he chose the one that for the first half an hour was an increase and then was a steady pace from that point on. Can we do it? That is one of the very final questions. Can we do it within a model where we assumed that our formulation is for the case of a constant center of mass speed? And here clearly we are increasing our speed, very little, but we are increasing. So one of the key things when we choose to violate the assumption of a model, which is very common in physics, in modeling, something we do all the time, we want to know how much this violation of the assumption is making our models invalid, or maybe at least errors, how much, and so on. So the thing that I would like you, I don't know, you cannot probably see from where you are, but I'll tell you, the average speed per lap here, starting at the beginning on the second lap, is 415, and then finishing at 460. That's the total average. The one per lap starts at 415 and finishes at 510. The power needed to increase your speed by a little bit every lap is in each case about 0.4, less than half a watt. So the idea is that if it's less than half a watt to increase it, I'm still basically within the equilibrium, to use a thermodynamic type of analogy. I am still within the equilibrium in which I created my model, so I can allow myself to study a formulation where we have a gentle increase of speed and the results are still trustworthy and we can do this. And for instance, the typical thing, I don't know if you can see that. So there's the distance covered every lap to 50, then 500, and then we end up on the 228th lap at 56,792. And the thing that the coach would have and would be able somehow to let the rider know how the rider is doing is the time per lap. So the time per lap, just to give you an idea how much one decreases the time per lap, since you might not see it from the distance. On the second lap is 16 seconds, 0.37, and on the last lap is 15 seconds, 0.25. So increased by about a lap, by about a second over 16 seconds. It is an increase, but it's not a dramatic increase. And that's why the model that's created for a steady state can still work well in the situation where our speed is changing. Here you can actually see how it comes about. The formulation of the kinetic energy, 1/2 mass times velocity squared on the next lap minus velocity squared on the previous lap. And this quantity is very small. So that's why it becomes something that is sufficiently small that we can use our model, violating slightly our assumptions. And now the last slide. Again, those of us who were close to Filippo, when he finished this, we seem to have heard that he said, è chiaro che tutto questo è possibile solo grazie a modelli matematici. It's clear that all this is possible only thanks to mathematical modeling. Thank you very much. Should we show once again this, are you about to do it? To show once again this 1 minute thing, so people can know it now that you've seen it more. You can actually see how close he follows the black line. Another assumption that is broken to some extent, but you see the black line that he used to follow? You can see the position being steady is rather a good assumption. He hardly moved even his hands. And here is the coach. You can see here as he passes Marco Villa, the coach of the Italian track team, and he's letting him know the times. Here he was with an iPad below showing the time for that lap. Here you see he's showing the time with an iPad. He's supposed to finish the last lap even though he covered an hour. That's the rule. And then he's off. Wonderful.
All right. Would anyone like to start us off with some questions? Sure, Art.
I guess the idea was that he should have done the decreasing lap times.
Yes.
And I'm wondering, so was he able to? Did he succeed in doing that?
He did, although he did have sort of a crisis after about 3/4 of an hour, and his speed decreased, and then he picked up again. So from the clinical point of view, the performance of Dan Bigham, who did the hour record before and was focused on the hour record alone, not quite, because he also is a great champion on the velodrome now, but he had more focus on our record. He was following that more closely. Filippo having a lot of other things to do from the point of view of road riding and so on, was not able perhaps to follow it with the same accuracy that would have been optimal.
A second question I have is about, I was kind of confused about the black line. Are you forced, the rule is stay within so much of the black line? It's just, or is it stay out of the blue area?
Stay out of the blue area, which is called the Côte d'Azur. That's the name that's given to it, because that's the time when you sort of finish your ride and you want to relax and unwind, you go to Côte d'Azur. But you are not, and I don't know if you saw it, there are those foams. If you want to show it again, there are those foams that are shown there. And you are not supposed to, you can go over those foams though, but that slow you down more in a way like in the hurdles. You see the foams? Those black things there, they're made of foam. So if you go over them, it'll take more power out of you than if you just cover slightly longer distance. In a way, it's similar to the hurdles. Nothing is forcing you to jump over the hurdles. You can just go and crash through all the hurdles, but you find that jumping over them is something that's preferable from the point of view of shorter time for the hurdle, for the race. So those sort of, so he cannot go, he can, but that's what protects somebody cutting through too much.
So the reason I ask is because I wonder if following the black line is actually the best thing to do. And where I'm coming from is that when you run road races, I'm not a real runner, but I've had conversations with people, who do 10Ks. And the conversation is, when you're going over hill, what's your best strategy? Maybe you try to maintain constant speed because you want to avoid fluctuations in your air resistance because of the BQ. But then some people say, no, it's actually better to speed up ahead of time because, and maybe it's a physiological thing, maybe you can recover on the downhill part. And some people actually argue the opposite. So maybe this is more of a physiological thing.
No, I don't. Well, perhaps, but we can put some assumptions, but this is not the same. We did do those calculations. For instance, when you have a time trial, when you go out 10 kilometers and back 10 kilometers, and it so happens that you say go out against the headwind and coming back with a tailwind. How should you do that? You should go harder against the wind and easier on the way back. And you can calculate it mathematically from classic optimization, the Lagrange multiplier. You introduce it as a Lagrange multiplier in optimization within constraints, and then it can show you that if your power that's available, say average power that's available is 460, then go up with a power, say, of 510 and come back with a power 410. So as to give 460. This you can do. Here is different because here what you would be doing, you would be covering extra distance and lifting and going slightly up. That's something that's very difficult to argue sometimes, and I know that this is online, so I might have comments from it from some coaches. For instance, in the velodrome of Bordeaux, there is a line that is called there the Belgian line, where they say that on the straight go slightly up and then come down towards the curve. From the physics point of view, and even I would say from the cycling point of view, it doesn't really make sense. If the velodrome is well designed, your optimal path is the straight line. By well designed, I mean that the transition curve is well done, so you don't have to get a jerk or jolt, depending if you are in England or in the United States or Canada. So then you just follow the black line. It's different from the situation of an uphill and downhill, or analogous to the case going against the wind and with the wind.
Okay, that is what I expected. That's why my question, I think, might be more physiological. So physically, you're saying the optimum is the black line.
Yeah.
But I'm just wondering, physiologically, maybe the optimum is not the black line. Like maybe it's worth it to actually pedal a slightly longer distance than you have to, because you're only credited for the black line.
Right.
Because you're taking advantage of the ups and downs, because physiologically, you can use that periodicity
for recovery.
Leverage, yeah, something about
for recovery. Yeah, that's something that I would have to. That's why I'm glad I can sort of pass the question to the physiologists. But mathematically, it wouldn't make sense. But yes, of course, it might be something that, from the point of view of that you recover in a certain way by going down and you keeping that. Absolutely. Absolutely. You actually do feel on the velodrome quite well that when you get into a curve, you are recovering, because you are leaning and all of a sudden you are covering distance that's lesser than on a straight. On a straight, your center of mass and wheels cover the same distance. On a curve, your wheels, which what you are credited for, cover more distance than your center of mass. And you feel it. You feel that you have the curves, and there are moments of respite.
Anyone? Another one?
Peter?
Very interesting talk. So, are there any rules regarding the design of the velodrome? For example, someone had the resources.
Right.
They build a very small
Mm-hmm.
velodrome to take advantage.
I mean, for this, we could maybe even connect with Theo, my doctoral student, who wrote this paper about the velodromes. I'll just say a few things, and maybe then Theo can connect. I don't know how to do it, if you know how to do that. There are regulations to a certain degree, so you have quite a bit of freedom. Within the regulation, you have quite a bit of freedom. They're supposed to be two straight lines, but the length of those straight lines is not necessarily decided. So you can try to make them quite short, but you cannot make it a circle. So you would be leaning always, and your center of mass would be covering a different distance. 250 became a standard now. If you made a velodrome that's smaller, the one that we had in Canada for the Olympics in 1976, in Montreal, I think it was 275 meters. So that's, but now it's basically, standard is 250. But if Theo is here, if he wants to say something, Theo, are you here?
Yeah, hold on. Let's see. Theo.
Testing 1, 2, 3.
Yeah, we can hear you.
Hello, everyone. Greetings from St. John's. Could I be reminded of the question?
How much flexibility, how much you have for the velodrome, for the design of the velodrome? How different, if you had money to just create a velodrome specifically for a given rider, for some performance of a type, how much flexibility or freedom of design you have for a velodrome?
So there are several, in the regulations, there are many restrictions. One of them being that the lap lengths, the length of any given lap, you have to have an integer number of them to amount to 1 kilometer. This is one of the reasons why 250 or 333 are preferred distances. So then you also have restrictions such that the straightaways must be parallel to one another. The midpoint of the straightaways is known as the pursuit line. It has to be in line with the pursuit line on the other end, on the home straight and the back straight. Beyond that, there are other rules and regulations pertaining to, say, the maximum steepness, the minimum steepness. The velodrome itself has to be smooth, but from a theoretical perspective, there are a lot of design options. And the paper that Michael had presented there, indicating the archive, it's in the final stages of the peer review and will be available for people to see. And therein, I have a lot of details about design considerations, so to speak.
Thank you, Theo.
Any questions?
Peter, did I answer the question?
But now I'm scratching my head about the integer thing, because if you can have a real number of meters each lap, I think you can have any integer number you want.
Well, I think that is an easy connection because Calgary is 400, so it's 2.5 laps to a kilometer. And the one in Milan, Vigorelli is actually just short of 400 because they made a mistake while building. So one has to add a little bit to it. But yeah, it doesn't have to be integer as such, but it has to be a nice combination that goes into a kilometer. Thank you, Theo.
You mentioned the fact that the air resistance is proportional to each square.
Yes. The force of the air resistance. The power is to the cube.
Right.
Yeah.
And for that reason, probably the cyclist has a dress
Of course.
that is very good in there.
Absolutely.
And people know what to do in skiing. And
Very much so.
now, why did he have nothing to cover his legs? The legs were naked. And naked is
Very good point.
less air resistant.
Very good point. I mean, that's something that they should be considered, perhaps. If Dan Bigham is here somewhere, Dan, as an INEOS engineer, you can perhaps comment on it. And the previous record holder as well. I agree with you because I just thought that this moment of the swimmers, it's almost more strange, at least, to see a swimmer swimming with a full body suit precisely for the smoothness of going through the water, which of course has more viscosity than the air. But would it be to keep cooler? I don't know. Or is it just a tradition that cyclists would have those shorts halfway through the thigh, and but a full length would be a better thing from the air resistance? An excellent point. Thank you.
But the swimmers are the reason for the difference in swimmers is much less the square of just the force.
Yes.
It's the fact that the changing velocity comes into play, and that's with the cube.
Right. It's the change of velocity. Here we are studying this. Yes.
I'm wondering whether the change of velocity of the legs.
That's right. That's right. Of course it does, and that's an excellent point that you bring, because, for instance, in our model, we are studying a cyclist as a translational concept. We are not taking into account, we did look into it, we do not take into account the rotation of the wheels or the rotation of the pedals and the legs. It's basically like if a cyclist was a translation along the velodrome. But absolutely, if the speed of a cyclist is near 60 kilometers an hour, then with the legs moving, it's even more than that, significantly more than that. I will follow up on it. And is Dan by any chance? No, Dan is not there. He's, as I was saying, the UK team is now in Toronto on the velodrome for the competition. So probably he's either training, competing, or resting.
I have another question.
Yes.
I was a track and field athlete, and track and field has kind of a similar problem with how you go from the straight into
Yes.
the curve. And when I was an athlete, they had two solutions. One was a solution to just make a semicircle,
Yes.
and one was a solution that was a changing radius a little bit
So-
higher at the beginning and lower at the end, in the middle.
So like a transition curve, precisely like this transition curve. So you wouldn't have an abrupt change of curvature from radius of infinity along the straight to a finite one along the circular arc.
And I don't know what it is now, but what would be best probably.
Oh, I think it has to be done. It has to be done because otherwise you cannot, you just cannot follow. In the case of track and field, you cannot stay very close to the inside of the first lane. You would have to move out from it. Yeah. So that's precisely this transition curve that's included there. That actually is something that one looks into. There's in some ways there's nothing new in the world. I like looking at the old things, and a lot of that was done almost 2 centuries ago when the railroad started, and they started to build the railroads. And in England, this curve was called the easement curve because it eased a transition from a straight to the curve. And one would look at papers from, say, 1870s, and one finds a lot of those calculations of the easement curve. So we should always pay attention to our ancestors who've done a lot, sort of, for us to do things that we are doing now. Yeah, absolutely. That's a very critical thing. So that would, of course, make a difference for speed. Maybe a 400-meter runner that would be important. Maybe 800 meters. By the time we're going for a longer distance at a slower speed.
For the relay.
Ah, I see.
But the change of the baton
Yes.
is right at the beginning of the rotation.
So 4 times 400. 4 times 400. Yeah.
4 times 100.
Oh, yes, of course, because, well, at the beginning of the curve, the end of the curve, beginning of the straight, yeah, of course. And the greatest speed, of course, for 100. Thank you. Oh, that's a wonderful, thank you for this information. Great.
Jimmy, you have a question?
Oh, great talk. I was just wondering how, so you calculate the average power needed to break the record. How was it used in the training and during the race? Like you mentioned, there was feedback from the coach on the time, but was there also feedback on power? Or?
No, it would be too much. In a way, you wouldn't be able even to, your brain is not working well enough. So it all goes by the time of the lap, slightly up, slightly down, or keep it steady. The idea is done to a large extent on a stationary bike when you are measuring the power that you can achieve, and you try it many times. For instance, Filippo tried half an hour before the hour record that he did. He did the summer before, did half an hour, and the information was brought from there. Dan Bigham did actually 3-hour attempts within the last hour. And he went for the full hour with all the information, with all the speeds, with everything else. So in that sense, you do it in preparation. You don't do it during the race. Actually, you are not allowed to do it during the race. Not that the rule says that you cannot have a power meter here or a cyclocomputer at which you are looking. The things can be measured. They are generally put behind the saddle. So afterwards, the coaches, you can take a look at the result, but you are not allowed to do it during the race, which it's a rule that's a rule, but it's almost unnecessary because your brain is not there to be looking at your power meters and deciding whether you should go slightly higher or lower, but it's in preparation.
Okay.
Which then gives you the times per lap.
Yeah.
Which is what the coach can see very clearly. You are slightly up, slightly down.
And so what was the power trajectory that the rider ended up using? Was that a constant or an increasing, as you mentioned, with temperature, or?
Sorry, I didn't. In what?
What was the strategy in the end? Was it the constant power, or was it an increasing
No,
power?
the power was slightly increasing, so as to decrease power, because whenever you are increasing, this is a correlation that's direct. It's not a correlation, that's a causality. If you are increasing your speed or decreasing your lap time and remaining in the same position, you are necessarily increasing your power. So the power was increasing, and the power was increasing quite significantly in some ways, say from 420 to almost 500. And the idea was to keep it a steady increase. But as I said, in the case of Filippo, there was a moment of weakness when, I mean, he was still way ahead of the record, so he was doing that very well. But there was, with a quarter of an hour to go, there was a bit of a increase of lap time, and then he picked it up. So it was, in that way, was suboptimal.
I see. Maybe I missed it, but how did you determine the slope of the increase in power?
How do you?
How do you determine how much the power has to?
Oh, from the model. From the model. It's not directly from the slope. I mean, if you are doing a slope from a mathematical point of view, if the difference is between, say, 55 kilometers an hour and 59, then a lot of things are linear. So you can assume things that you follow the slope, and the slope of the increase of speed would be proportional linearly to the increase of power, but it's actually more complicated than that. So you simply calculate your power. So it's all the algorithmic thing. It's actually computationally is quite intense to do this thing. So sure, one can have the rule of thumb and some quick thing that one can calculate, but it's quite a complicated model that you see. That was the speed at the beginning, and then the speed progresses that way. Then that's how. I don't know if you saw this, if you remember this graph of power that is going up like that.
Yeah.
You don't see it exactly, but it's actually slightly concave up. It looks like a straight line because we're only looking at a difference between 55 kilometers an hour and 59. So it's a very small change in power, but as a matter of fact, it's slightly concave up. You just go into the model and you do the model that we did in MATLAB. Theo did quite a bit of it. So it's done in MATLAB, and then it cranks through. It takes a while to crank through to give you the power.
And this is including the temperature, the body temperature, or because what I got from it is that if the temperature matters, you don't want it to be too steep, because then, sure, you want it to be steeper than you would. The
temperature of the body. Yeah. You are talking about the core temperature. Yeah. You want to start more slowly, so as not to heat up your body too much.
Yeah.
By putting too much effort at the beginning. By the way, I didn't speak very much of it, but as far as the temperature of the velodrome, we set it up at 27 degrees, which is warm. But it makes quite a difference as far as power needed. If you wanted to, say, cycle in a more comfortable temperature, 21 degrees, you would be significantly increasing the average power necessary, because you have rho, the density of the air would be higher, multiplied by the speed cubed. So, of course, it depends on an athlete. If an athlete says, I cannot handle 27 or 29, I really want to have a temperature down to 21, sure, but as I said before, there ain't nothing free in physics. So by that physiological comfort, you'll be paying with more power needed, and not trivial amount of power if you want to drop it from 27 to 21, say.
Okay, thanks.
Right. So it's 4:50 now, so I'll have a pause to let anyone leave who wants to leave, and then we can resume afterwards. Okay, everyone's staying.
I'm delighted. I'm delighted. Thank you very much.
I was wondering about the black line again versus the assumption that you include of the gravitation from the inclination of high school. And it looked like there was quite a bit of deviation from the black line. And so I'm wondering, like, the toss up here between these two, like, is there potentially some way of, putting some variability around
the model? Absolutely agree with you. One can do more of an empirical model in which one would add those things. And one can even say that even though the lap time is 250, a typical ride would be maybe 260, maybe not 260, but maybe 255. You would add half a dozen meters, let's say vaguely, to your 250, and then you would have a propensity to add it more when you're coming out or when you're getting into the curve. So definitely, models can be adjusted, and model is just a model, and it should be taken as such. Is an analogy of physics. It is by no means an expression of physics. So I completely agree. Actually, my brother and I, he's one of the co-authors on the paper. He's in Calgary. He's the head of the Department of Physics at Montreal University. So if you're interested in talking about that, you have somebody right in Calgary to discuss those things. We talked about it. He was the one who thought, maybe one should do sort of an empirically driven model a bit when we don't stick to 250, but we include those deviations. And of course, that would depend on an athlete too. Some athletes are more capable to holding that line. Some athletes are less so. So you would have some parameter within the model depending on how accurate the athlete is in following that. Absolutely agree.
But wouldn't the correction be very small because it goes cosine?
Yeah, the correction would be small. So then the typical thing to do, of course, would be to do the sensitivity analysis and to see how much we gain by introducing an increased complication of a model, how much we are gaining as far as the accuracy. Absolutely, yeah.
I guess with relation to pacing strategy, another assumption you have is that mechanical efficiency stays the same for 1 hour. But I guess as the rider approaches the end of 1 hour, mechanical efficiency will get worse. I wonder if that's something.
But why would you think? Because mechanical efficiency is really our hubs, our bottom brackets. Why would you think?
Or sorry, so the assumption with related to the bike's efficiency, I think you said.
No, it's only efficiency of a bike.
Or
It's
there was that efficiency that you said was this going to be around 98%. I guess.
Right.
Yeah, what I'm referring to is the relationship between metabolic work rate and then the mechanical work rate. So the 460 watts in the beginning will have a lower metabolic work rate than the requirements near the end.
If I understand correctly, it's a physiological question, right? So, yeah, I think.
But I wonder, potentially might want to consider mechanical efficiency and then pacing it.
And somehow included. I completely agree with you. Actually, I was so it would be very nice if we can think about those things more. And that's, just a rhetorical statement of Dan Bigham that half an hour is not half of the hour. That your second half an hour is something very, very different. And you have to. So that's this efficiency of your physiological capacity of producing that power, right? And what you are suggesting that one can use some coefficient to include it somehow, to put a physiological context onto it.
Yeah, possibly.
Yes.
For a better pacing strategy.
For a better pacing strategy. Actually, an interesting thing was, and I don't know if Chris is there from Core, the company that makes those heating devices, or the one that measured the heat of the body, which, as I said, it's very simple as a device. It might be complicated as far as the apparatus, but you just put it at the same place, or just next to your heart rate monitor on the same tape. And how much you are gaining by keeping your body temperature low for longer, but you have to pay for it by increasing the pace towards the end of the race or during the race. So that's something that is combination of physiology and physics, mechanics. I think there is quite a territory for research and for study there that I hope Theo, if he's still there, that he will do as part of a postdoc.
I think ideal situation is to minimize the weight of the velodrome and also the rider. Is that right?
Say again, please.
I think ideal is to minimize the weight of the velodrome and also the rider.
Yes.
So in one slide you showed that total weight is 96.
Right.
Can you tell me how much was from the
Well, the bicycle was extremely nice. It's a Pinarello bicycle, and it was actually, although it's an Italian make, it was made in the UK, or the frame was made in the UK. The power meters were done in Italy, in Veneto, but it was 3D printed. The bicycle or the frame itself was 3D printer. Sure, you can make it a little bit lighter, but I don't know if it will be necessarily that much of a difference, because once you launch it in a speed, that might not make much difference. Now, as far as the cyclist, to make, Filippo is 193 centimeters, so he's a tall person. So the weight is not, he's by all means very slim, but it's more of a physiology than, again, that you start to lose weight to be lighter, but you cease to have the power. It's quite common in road racing that somebody wants to get better in climbing the hills for Tour de France or Giro d'Italia, and then they become less good in time trials, in flat time trials, because they lost a lot of weight and they lost power that would be necessary on the flats. So there's a trade-off there. Sure, if you could lose weight without losing power, then that would be better. But it's always an optimization.
And is there any study on the technique for pedaling? Because from theoretical point of view, the force should be perpendicular to the crank. That's the force.
Yes. Yes.
Any sliding force with respect to crank.
That's an excellent point that you make. And by the way, the Favero power meters, the Assioma, they are two models. And if you want to get slightly more expensive one, you will get one that has independent power meters in each pedal. So then you can see, for instance, what is your combination. If one leg is stronger than the other, you can see that as well, that you should perhaps work on your right or left leg to make them equal. It also does the speed of your pedaling. It uses the gyroscope in a manner that it will tell you what's your speed of pedaling when your pedals are vertical and when they are horizontal. When they're, the horizontal, it's a bit faster. So it's not just doing an average cadence and telling you an average cadence, but it actually shows you the speed of your pedaling. And it shows you another thing, which is very nice. It's actually nicely shown on a diagram, where you give more power. So you are giving more power, say, if we think about the pedal as a clock, you would give more power, well, going counterclockwise, between 10 and 7 on a downswing, and then less power when you are at 6 at 12 with your pedal. So all those things appear on those measurements with reasonable accuracy. In case of Filippo, his cadence for the hour record was 96 revolutions a minute. That was his average cadence. And that is also depends physiologically. Some riders would prefer to have a lower gear but higher cadence. Some other would be okay with the higher gear but slightly lower cadence. But it would be always, say, from mid-90s to 105 or so. That would be the cadence that would be optimal for most of us. Another thing that enters in it is how long of a crank do you want to be using? About 172.5 millimeters, 165, too short for longer rides. So there's a lot of things that come in.
Follow-up question was that is there any regulation regarding the ratio, like front and back?
The ratio of?
The gear.
The ratio of a gear. Yeah, the ratio of a gear. Right now, the gear, the gears are used quite substantial big gear. So I mean, basically your chain ring now is into 60s, 62, 64 teeth, and the one in the back is about 15 or 16. So you are doing that kind of a formulation. So the development, as it's often called in the UK especially, which means how much your bicycle goes forward with one revolution, it approaches 10 meters. So with one revolution of the pedal, you are going about not quite 9 and quite a bit. You are going almost 10 meters forward. And of course, it's a fixed gear, so you have no way to change it. You cannot start, or you cannot, so you have to decide on what's your what would you do? Generally, for a ride of the hour, you would make slightly bigger gear. If you are doing a pursuit of 4,000 meters, you would go for a higher cadence, but slightly shorter gear. Yes?
I wanted to ask about that idea about the mass being lower is better. Is that absolutely known to be true, that lower is better?
Well, if you look at the formulation of the model, you would see that, for instance, the amount of power you need to lift your center of mass, you would have less power needed to lift your center of mass. Then your resistance of the rolling, it's still multiplied by m times g. So smaller m would mean the resistance, the coefficient, the part of the summand of your model that includes the resistance of the rolling would be less if your mass is less. So from the point of view of purely physics, yes. But if you get somebody, but we seem to feel it or have it, that would be a physiologist who should answer that question, not me, that if one loses too much weight, one starts to lose power. And then there's a trade-off that, sure, I am requiring slightly less power to do that effort, but I lost more power than the difference of gaining of benefit.
Well, the reason I ask is because, in a way, higher mass would help you have
inertia
fluctuations in the velocity.
Would have inertia, yeah.
And so, of course, you pay in the beginning because you have to accelerate.
Right.
But if you had infinite inertia, then the person could follow the prescription, which is to have steady power, right?
Right.
And they would have steady speed. And
I agree.
The fluctuations would ultimately be hurtful because of the VQ.
I completely agree with you.
Also, just in general, in sort of cycling, the idea that you need a light bike has kind of been thrown upside down in the past few years because people always obsessed about getting light
sure.
bikes. And then past few years, they've shown in many different kinds of experiments, some of them pretty well controlled, that if you have a trade-off between an aero bike and a light bike,
of course,
you prefer an aero
of
bike.
Of course.
And so,
and
that's even in a real, a situation where they are climbing.
Absolutely.
So,
but you notice that when you have a time trial that starts on the flat and finishes on the up, there's going to be a very nice time trial like that in Giro d'Italia this year. Probably most riders will change their bikes. They'll be going with disc wheels for the flat part, and then they feel that it's worthwhile to spend time getting off the bike, getting on another bike, to have a lighter bike without disc wheels on the way up. I agree with you that obsession of the weight among the cyclists is excessive, or was excessive, still is excessive probably, and especially on a velodrome, you put the two disc wheels front and back, which are heavier than if you had very thin spokes, which would be, from the point of view of performance, on the smooth velodrome would be absolutely fine, but the air resistance from the turbulence around the spokes would be more costly than extra weight. There's another interesting thing, for instance, that something that has been measured too. I don't know if Robert Chang from California is here listening to us. If you are, Robert, say something about it because you are the specialist of it, that you draft yourself. On a velodrome, you draft yourself. What do I mean by that? When you start riding and you say after a dozen of laps, you created yourself somewhat of a whirl, somewhat of a movement of the air, that you are now following your own draft. In a way that Robert measured that, and for the same speed, the necessary power would drop by a few watts after, say, a dozen laps. So one of the things that we insisted, that even if Filippo or Dan before is on the opposite side of the track, nobody crosses the track so as not to break this movement of the air, which is probably just a few meters a second, but that means that with respect to the air, you are not moving at 56 kilometers an hour, but 53 kilometers an hour. So even that is something that has been considered And one of the reasons not to allow too many people on the track, and nobody allowed to cross the track when the rider is on it.
So maybe they
Peter?
should make the bike less aerodynamic so that it creates
Right,
more
right. Of course, one can definitely do that to make a, or what one could do, which I don't know if that would be legal, is to say get a bunch of riders on the track before, who would sort of create the whirl, and then the hour record starts once the thing is already moving. But
get really good air conditioning.
or get particular, yes, yes. Well, that was known. I guess most of you are too young to remember. Not you, Peter, to remember to remember the Olympics in Moscow, that the Soviets would be opening for the javelin. They would be opening the gates of the stadium, so then the wind or then the air would pick up the thing and carry it better.
They did the same thing in Sydney, but they had the wrong direction.
Oh. Very interesting.
Sydney had no world record for track and field.
Yes.
Because the wind was going
in the wrong direction. I see. So yeah, so there are those sort of things.
So just to reply to that about the mass.
Yes.
I think it would be interesting to take a person trying to do constant power, but with some imperfections, some fluctuations, and feed that through the model to see whether low mass is indeed the optimal.
Yes, one could definitely try that. And as far as the mass, it's so nice that we can speak for a while here, because I was not able to say too many things. I said, I think a lot of things may be a bit boring after a while, but I can add a few maybe less boring things. With Dan, with whom we were doing this very carefully, preparation was done over about a year. We would measure his weight when he gets off the bike. And Dan is smaller than Filippo, but not small, 183 centimeters or so. And he would be losing about 2.5 up to 3 kilos during the hour. Mostly the water, probably, but he would be losing a significant portion of his body weight. So we actually did have in our model a formulation that the mass would not be constant, but almost like in the theory of relativity, the mass would be changing, not with speed, but with time. So we would have a decrease of his mass by a couple of kilos or 3 kilos over the hour.
So I'd also like to suggest a cheat, which I'm sure is against the rules, but I think it would be a way to break the hour record. Is that it's been shown that you can, of course, sail downwind faster than the wind, or you can sail directly upwind.
Yes.
And then the trick is, I don't know if people are aware, so there are great videos on this, but it's basically a fancy sailplane or sailboat or sail bike, where you have a propeller in the air and you have a propeller in the water or against the ground. And so in cycling, I think the analogy would be you have 3 velocities: ground, rider, and air that you can work against. And so the idea is you're pedaling both something that cranks the wheels, but also cranks the propeller.
Would it be allowed, as you said, this would be
So
illegal?
I'm
yeah.
sure it would be illegal, but the idea is that it's essentially the same thing as sailing downwind faster than the wind.
Yes.
Is that it should be possible to go.
Probably there's one can, there's also the regulation of a bike are quite strict. What you can do, even how far forward you can be leaning, those things are set fairly strictly. And you are not supposed to have any device that will be covering your face. And there's, of course, also the recumbent bike, and people do it on the recumbent bike. And I would recommend on the recumbent bike, which is all covered up, is significantly more. I don't know exactly how much it is, but it was also done in Grenchen in Switzerland, and it's around 80 kilometers, or maybe slightly over 80 kilometers in a bicycle like that, in a covered bicycle.
All right, 4:35. I guess we'll end it here, but anyone feel free to stick around and chat, and let's thank our speaker again.